Hello friends, my name is Aviad Rubenstein. I'm very excited to share with you this awesome story based on joint work with Elazar Goldenberg and Barnes Saha. Our story is mostly about edit distance. Edit distance is defined as the optimal number of insertions, deletions, and substitutions to transform a string x to a string y. Given the x and y in the example, the optimal transformation, which is g to an a, that deletes the t from x and deletes the t from y. There's a quadratic time dynamic programming algorithm, and it turns out you cannot do much better assuming a strong exponential time hypothesis. To overcome this quadratic barrier, there is a long line work on special cases such as small edit distance, and also long line work on approximation algorithms. We'll talk about both later. The holy grail for both of those is to overcome the quadratic barrier and get as close as possible to linear. Sometimes even linear time is not fast enough. Our favorite application is bioinformatics, computing the edit distance between DNA sequences. And as you probably know, if you've ever been to a talk about edit distance, DNA sequences are really long. So we want sublinear time algorithms. And there is a line of work on approximation algorithms that work in special cases and run in sublinear time, so faster than what it would take to even read the entire sequence. So there's lots of work in this. It sounds great. There is a downside though. There are some obvious limitations. For example, if the actual edit distance is delta, we might not see any errors, any differences between the two strings faster than n over delta time. And this holds even for easier metrics like the Hamming distance. If we can solve this problem in n over delta time, that would be great. The state-of-the-art algorithms are much weaker. For example, they tell us how to distinguish between edit distance delta and delta squared. That's a very weak approximation. Perhaps more importantly, it's not clear what's the point of having a sublinear algorithm. When we construct the string, we have to sequence DNA, and that probably takes at least linear time. Now, let me tell you the real story about sublinear time algorithms for edit distance. We have a lot of strings, and we might spend linear time sequencing the DNA of each of the cats in the picture. But once we have the string, we want to compute a lot of pairwise comparisons, and we want each distance computation to take sublinear time. If you have a fast algorithm for computing a lot of pairwise comparisons, you might, for example, be able to reconstruct the family tree of all these cats. Here's a very timely example of a family tree of variants of the coronavirus. And here's a very important example of a family tree you really need DNA sequences to construct. Enough with silly applications. Let's go back to talking about actual algorithms. We have a pre-processing step comparable to the sequencing of the DNA. That might take linear time, maybe even more. And then we have a lot of pairwise queries that want to be as fast as possible. Before we continue, I want to mention there is another line of work on approximate nearest neighbor with edit distance metric. The focus there is on the other extreme case where the number of sequences is much larger than the length. Whereas we focus on the case where the number of sequences or the number of pairwise comparisons that we want to make is within polynomial factor of the length of each sequence. So here's a formal model of edit distance with preprocessing. We preprocess each string separately. So Alice the ocelot is going to preprocess her own DNA sequence. The bobcat is going to preprocess his own DNA sequence. And then in the query step, we're giving both strings and also the output of the preprocess. We want to compute edit distance. The main question that we ask in this work is whether preprocessing can help. Disappointingly, in the worst case, the answer is no. So there's a 4-chlor-ish hardness results that we formalize that, assuming strong exponential time hypothesis, the same kind of lower bound of quadratic time holds even after polynomial time, arbitrary polynomial time pre-processing of each string separately. Furthermore, we don't know yet whether there is a 1 plus delta approximate algorithm that runs in subquadratic time. But if you had a 1 plus delta approximate algorithm that runs in subquadratic time with arbitrary polynomial pre-processing, then you can get a 1 plus delta approximate distance algorithm that also runs in subquadratic time without any pre-processing. So can pre-processing help? Well, actually, it can help in a lot of interesting cases. Consider, for example, the small edit distance regime. So we devise an exact edit distance algorithm that runs in pre-processing time near linear, and the query time is nearly quadratic in delta, in the edit distance. For example, just to give you a comparison, without pre-processing, the state of the art is a delta versus delta squared approximation, and it runs in slower time, so delta cubed, and there's n over delta, which is unavoidable. I should mention, order delta squared is tight, assuming strong exponential time hypothesis for exact algorithms. Our second algorithms consider LCS between, or longest common subsequence between two permutations. It's the analog of longest increasing subsequence, except increasing subsequence doesn't really make sense in the pre-processing model. And here we can improve the running time from algorithm 1, and the query time is linear in delta in the distance. We also have new approximation algorithms. For example, we can pre-processing the two strings in roughly quadratic time, and then compute a 7 plus log of 1 approximation in roughly n to the 1.5 time. For comparison, without pre-processing, the state of the art in this n to the 1.5 time is some very large constant. We also have an algorithm that works in a model that I really like, where you pre-process only one string. So here you can think of having a large database of strings you already pre-process, and now you have a fresh new query. Here, our algorithm is pretty bad. We have a delta versus delta squared type approximation, but it still beats the state of the art for no pre-processing in non-trivial way. So this is a proof of concept. I'm really excited to see future work on this model. I told you that pre-processing helps. You might wonder why. So first of all, there is this annoying lower bound of n over delta characters. We have to read at least that many characters to observe any difference between the two strings. We obviously overcome that because in the pre-processing step, we read all the characters. More concretely, in algorithms 1, 2, and 4 that work in the small edit distance regime, the pre-processing step is simply a computation of hashes of contiguous substrings of each string. If the strings are very close, small delta, then that means there are large substrings of string x that exactly match to large substrings of string y. Given the hashes, we can very efficiently find those matches. The approximate edit distance regime, our pre-processing step is also very simple. We simply compute pairwise edit distance of contiguous substrings of each of the strings separately. This kind of algorithm is this kind of pre-processing is very helpful for recent line of work on approximate edit distance algorithms that use triangle inequality. I'm now going to show you an overview of algorithm 1. Before I show you, I need an important warning. The algorithm is so simple you might actually understand it. So, warm-up step 0 is just a classic n-squared dynamic programming algorithm. We have a n by n matrix where the columns correspond to indices to the string A, and the rows correspond to indices to the string B. And we fill the cells, we iteratively fill the cells of the matrix using this formula that you see here. Slightly more advanced, but still a warm-up, there is an n times delta algorithm due to Yukonen. Has a very simple observation. If we know the edit distance is only delta, we're never going to match a string character from the beginning of A to a character in the beginning of B. So we can ignore all the cells in the shaded areas and apply the same formula of dynamic programming that we saw in the previous slide. Now getting even more advanced, there is an n plus delta squared time algorithm. This algorithm uses something that's called the h-wave. Informally, you should think about it as how far in the strings can you go while making only h edits. For example, h equals 1, there is some curve of how far you can get, h equals 2, h equals 3, etc. Because the edit distance is only delta, we know that after delta waves, we have computed the edit distance of both strings. Here's how you use the h-wave for an actual algorithm. Step 1, construct a suffix tree. It's a data structure that takes both strings A and B, and the data structure supports queries given index I to string A and index J to string B. It finds the maximal D such that the substring AI through I plus D is exactly equal to B J through J plus D. Step 2 is a simple dynamic programming algorithm that iteratively computes the next H-wave. Each entry in each H-wave requires 3 queries to the suffix tree data structure and to the previous H-wave. Now that we're done with warm-up, I can show you our entire algorithm in just one slide. In fact, we use the same H-wave and the same dynamic programming for the query step. The preprocessing step, we replace the suffix tree, the required knowledge of both strings, with hashes that we can compute for each string separately. That's it. I hope I managed to convince you in the introduction that thinking about edit distance with preprocessing is the right question to think about. But even if you don't care about the preprocessing model at all, as a bonus application of our very simple algorithm from the previous slide, we get an improved no-preprocessing algorithm for approximate edit distance. So we give a 3 plus epsilon approximate edit distance algorithm that runs in times roughly n to the 1.6. This improves on 1.69, 1.72 from recent works. So to recap, we asked the right question, which is edit distance after you've preprocessed each string in a distributed manner, where Alice the ocelot can preprocess her string, and Bob the bobcat preprocesses his string. In this setting, the worst case is still hard, but we give much better and much simpler algorithms for very important special cases. There are lots of exciting future directions in this model. Just a sample of 2 obvious ones. One is better approximate edit distance with preprocessing only one string. We can slightly beat the state of the art, but possibly you can do much better. Another one is that we give exact algorithms whose query time is exactly quadratic in delta. It would be very interesting to understand whether we can use the recent breakthroughs on approximate edit distance to give approximate algorithms with preprocessing whose query time is subquadratic in delta. Thank you very much for listening.